Hello, everyone. My name's Jana Gersovich. I'm the outreach coordinator for Columbia Astrophysics Laboratory. And thanks so much for joining us tonight for our public live stream. We usually hold live talk and telescope stargazing events at Columbia University's campus, but we're moving to live streamed events and virtual planetarium tours. So please, we're planning to do more of these in the future, so please subscribe to our YouTube channel or our mailing list, which I'll put up after the talk. So in terms of the schedule for this evening, we'll start with the talk, Our Universe in Another Light. The talk will be about a half an hour long, and then we'll have some time for questions. So if you're thinking of questions while Kim is talking, feel free to submit them through the chat. And then after the talk is done, we'll answer some questions from the audience. And finally, we'll do some flying around the galaxy using Planetarium software. So I have with me Micah Asinapura. So
hi, everyone.
And he works on planetarium visualization at the American Museum of Natural History. And he'll be acting as our spaceship pilot for a planetarium tour. And I'm also lucky to have with us our speaker for the evening, Kimberly Arcand. She's a world expert in astronomy visualization and has been a pioneer in 3D imaging and printing and virtual reality applications in the field. Kim began her career in molecular biology and public health before moving to work for NASA's Chandra X-ray Observatory in 1998. So in addition to being an award-winning producer and director, she studies perception and comprehension of high-energy data visualizations in both novices and experts. So thank you so much, Kim, for joining us today.
Thanks.
And give us just one moment. We're going to switch over to Kim's slides and begin the talk.
Okay, I think I'm ready to go. Can everyone see my first slide? Okay, I see me, if that helps at all. Great. All set? Ready for me to start?
Go ahead.
Okay, great. So, hi, everybody. Welcome to tonight. I'm really excited to be here. I would have loved to have been there in person, of course, but virtual is the next best thing these days. So I'm going to talk a little bit about NASA's Chandra X-ray Observatory, which celebrated its 20th anniversary just last year. So Chandra is a pretty incredible piece of equipment. In 1976, astronomers proposed for this telescope that was at the time named the Advanced X-ray Astrophysics Facility, which was not the most catchy name, so fortunately it was renamed upon launch to the Chandra X-ray Observatory in name of a very famous Indian-American Nobel laureate in physics. And X-ray astronomy, I think, is really fascinating because it's looking at the very high energy things of the universe. So right now we're looking at a comparison of mirror types. That first mirror that you were seeing was essentially the standard optical type of configuration where the photons would be hitting the mirror straight on. That can't work in X-ray astronomy because they would just be absorbed by that flat surface. So for X-ray astronomy, we need to have these barrel-shaped mirrors because X-rays are sort of funneled down like at a grazing incident, as if you're skipping pebbles across a pond. So that's how the Chandra mirrors were set up, and they were, and still are to this day, the most cutting-edge X-ray astronomy mirrors in the world, and were so very smooth and perfectly polished and just incredible to give us the type of data that we'll be looking at throughout the rest of the talk. So the Chandra X-ray Observatory was launched back in 1999, and it was launched above the Space Shuttle Columbia, which was mission STS-93. It was the first mission commanded by a woman commander, Eileen Collins, who was just incredible for this mission. And Chandra was deployed soon after launch because Chandra is a pretty big telescope. It's about the size of a school bus. So for this mission, it was very heavy. And what a heavy telescope like that meant was that essentially it made the abort scenario is a little bit more complicated for the astronauts on board. So this was a slightly more dangerous mission than your run-of-the-mill mission at the time, and the astronauts trained heavily for that, and everything went perfectly. And in this image, you're seeing Chandra a little before it was sailing off on its way to work. So Chandra goes about a third of the way to the moon at its farthest point from Earth. What that does is it gives us a very unobstructed view, hours of observing time, which I think is really incredible. There are actually less X-ray photons in the universe, so we need a lot of observing time in order to be able to get all of that detailed information that we're looking for. So what types of things does Chandra get to look at? It gets to look at the high energy universe, as I mentioned, so things like exploding stars, areas around black holes, colliding galaxies, and of course, a lot more. It's pretty incredible, all of the different types of objects that Chandra gets to look at and has looked at over its 20-year plus lifetime. So Chandra fits into this bigger picture of the multi-wavelength universe. It's really important for us to be able to have all different kinds of light, all different kinds of information, to be able to understand more about what exactly is going on in our universe. So that's the full electromagnetic spectrum that we need, from radio waves all the way up to gamma rays. And you're probably familiar with many of these types of light in your life already, whether it's a microwave that you're using and you're using microwave light to disturb the water molecules of your food and heat it up really quickly, or using infrared light to talk between devices. And of course, even in medical, having X-ray light, for example, for your teeth or your bones. So Chandra is not like a medical X-ray machine because it's not emitting X-rays. Chandra is actually just observing the X-rays that these objects out in the universe are emitting themselves. But it's really important to look at all these types of light to help fill out the story. And today, of course, it's even more important to look at many different kinds of information in general. The advance of multi-messenger astronomy has become just incredible to witness over the past 20 years plus of my career, where you're now being able to see things or interpret things like gravitational waves in addition to neutrinos and cosmic rays. So having the electromagnetic spectrum in its full glory is really important for astronomy in general. And then having additional information beyond that is important as well, because each little thing lets you see something different. You can think of it like all the keys on a piano, right? So if you could only look at optical light out in the universe, you'd only have maybe middle C and a couple keys around it. It would be a very boring piece of music that you'd be playing. But when you have the full piano and you have all 88 keys to play your piece of music, to play your concerto or whatever it is that you're interested in, then everything starts to make sense and you can create something really beautiful. So just a very brief hiatus from astronomy. I love showing this picture because I actually really like bugs. But I started out in molecular biology, as Jana mentioned. I was interested in the stomach contents of things like this, a deer tick, Ixodes scapularis, though I realized I didn't actually want to study bugs for the rest of my life. But I was in this group of parasitic and infectious disease, which I guess is kind of relevant these days. But what I was really interested in was computers and using computer science as a tool to be able to extrapolate all of the information that we wanted from different areas of science. And specifically, it brought me here working for NASA's Chandra X-ray Observatory and getting to work on the incredible data that a telescope of this magnitude, pun intended, I guess, gets to produce. So ones and zeros are kind of my thing. All of the bits and pieces that go into making up these images of the universe, I think are pretty exciting. So I'm going to take you on a very short tour of the X-ray universe through my eyes. So some of the most beautiful objects that I've ever had the chance of working on, whether directly or tangentially if someone else on my team was working on it. Cassiopeia A was the first light image of the Chandra X-ray Observatory over 20 years ago. And it was incredible because you're looking at an exploded star here that is only about 1 hour's worth of information. And already from that first hour of information that we got on Cassiopeia A, you can see the very bright whitish yellow spot in the center of that remnant. That's the long sought neutron star that hadn't been seen before Chandra came around. And we're going to look at a whole bunch of different kinds of objects. These are heavily biased to my favorites. Most of what you're going to see are multi-wavelength in nature, so combining some combination of X-ray light with, say, optical light or infrared light like you're seeing here. So Chandra gets to look at so many different objects, as I mentioned, from young stars and baby stars, infant stars, tall towers of gas and dust, clusters of stars, to more mature stars and like globular clusters, stars that might explode someday, maybe in our lifetime or maybe not for 500 years or so. Stars like our sun that are on their way out. Stars that have obliterated themselves in these beautiful supernova remnants. Supernova remnants are my favorite, so I'm going to be talking about those mostly tonight. And you'll see these are my favorite here. Stars with the leftover cores left behind, and pulsars and neutron stars. Areas around black holes, such as the one at the center of our Milky Way galaxy. All sorts of galaxies of various shapes and sizes. And these are definitely one of the most exciting areas of research as well, getting to see all of these different types of galaxies and understanding what's going on. So galaxies in the shape of pinwheels, exclamation marks, cartwheels, rings, sombreros, starbursts, antennae, whirlpools, all sorts of shapes and sizes. Black holes, of course, as I mentioned, really important. So looking at the center of galaxies for their supermassive black holes, such as those that are merging like you're seeing here, or those that are shooting out these massive jets. And finally, clusters of galaxies, which are the largest gravitationally bound objects in the universe, and are also in themselves very beautiful. Some of them look like they have toothbrushes on them, and some of them look like they're smiling back at us. So all of the different things that Chandra has been able to look at, 2,700 trips around Earth in 20 years, 23 trillion bytes of data collected, 3.6 million lines of code written to analyze and operate and collect all of that information that I've been showing you. It's just an amazing telescope that it's still kicking after 20 years in that harsh environment of space. So back to my favorite things, all the ones and zeros, that binary code, that information that we use to talk to our spacecraft. How Chandra observes this type of information and collects it. You're seeing an object out in the universe, in this case, Cassiopeia A, that exploded star I mentioned briefly. That information, that light has been traveling from that object. Chandra points at it, looks at it, is then observing all of that information, packages that information up, and then sends it down to Earth in the form of ones and zeros before eventually it makes its way to our control center in Cambridge, Massachusetts, and eventually perhaps my laptop here in Rhode Island. It starts off looking like a table where every packet of energy, each photon that was recorded during the observation is essentially mapped out by the time, the location, and the energy level. And then we use this software to essentially create the visual representation of the object. So as you're seeing here, again, I'm coming back to that very favorite object of mine, that supernova remnant, Cassiopeia A. A supernova remnant is essentially a star much more massive than our sun that has started to run out of fuel, and it collapses in on itself, and then it explodes and just kind of vomits its guts out all over the universe. It makes for a beautiful bit of leftover bits and pieces. And after 20 years on the job, Chandra has looked at Cassiopeia A quite a lot. So now you're looking at, opposed to the hours observation I first showed you, now you're looking at over 1 million seconds worth of data, and you can see the difference. You're probably also seeing some of the optical star field behind it that we add. One of the things that we've found in our research is that having a visual context like this, adding that optical information, is actually really important for helping to establish the contextual information and the context of what that object is. When you have a lot of information on an object like Cassiopeia A, when it's been studied over and over and over, a couple million seconds from Chandra alone, not to mention across most wavelengths in the sky, actually all wavelengths in the sky. When you have something like that, then something kind of special can happen, and you can create a 3D model. This model that we're looking at here was the first time that observational data had actually been used to create a 3D model of a supernova remnant. And that was an incredibly exciting thing for me. This object and this study was led by Tracy Delaney, who was at MIT at the time. And she essentially used some basic geometry and the Doppler effect to be able to understand which of that light was moving away from us and which of it was moving towards us. And what you're seeing here is a combination of the Chandra X-ray information as well as some infrared data from the Spitzer Space Telescope, which was recently retired, plus some optical data from ground-based telescopes here on Earth. And that combination, that multi-wavelength power, really helped sort of show the benefit by being able to do this 3D model. The scientific benefit of having a 3D model like this was that scientists saw that this came apart essentially in two pieces, that spherical shell and then those bipolar jets that you're seeing. So once we had this 3D model, we were really excited to do all sorts of things with it. I should mention, this probably looks a little bit like a brain, and if you're thinking that, you are correct, because the first way that we were able to create 3D models like this with Chandra data was actually by using some software that some scientists at the Center for Astrophysics had borrowed from Boston area hospitals from brain imaging researchers. And that's why you're seeing this sort of clumpy sort of look to it. And when you have a 3D model, there are just an amazing amount of things that you can do with it. And 3D printing is one of my favorite. It was sort of a lark. I was very just intellectually curious as to what would happen if we 3D printed this model, this data set that we had, and it ended up turning into a full-blown program. We worked with people who are blind or visually impaired in order to improve these data sets and have them add more value. And we now have an entire tactile and braille kit of objects like this that people who are blind or visually impaired can explore. And it's probably one of the most meaningful projects I've ever gotten to be a part of. So it was a very big turning point for me. We've also used that same data and brought it into virtual reality and augmented reality and a number of different kind of extended reality projects, even holograms. That also was a revelation. It's been very interesting to be able to experiment with objects like Cassiopeia A to a different scale. Obviously, Cassiopeia A is going to be much bigger than anything we could ever fit into a room. The mass of this object, it's very big. So the surface area is about 40 million billion times the size of our sun and planets combined, and you can toss in Pluto if you're a Pluto fan. So in scale, this thing is really, really large. But it's interesting to have a different kind of device or mechanism to be able to look at that information and understand it in different ways. And we've also brought it into augmented reality, as I mentioned as well. So you can essentially build Cassiopeia A, build the supernova remnants by elements in your office or in your home, if everybody's homebound these days. And you can see in this case, we have it color-coded by chemical element. So you're seeing the green, for example, is the iron, and that sort of pinkish color is infrared emission. The yellow is some silicon, and a little bit of neon and argon are in there. So you can essentially build your remnant by elements through this augmented reality experience. And all of that, you know, has been essentially inspired by this first observation that we ever got of Cassiopeia A. If you had told me 20 years ago when I first got to look at this data that I would be doing that now with Cassiopeia A data, walking around inside it and holding a version of it in my hands, I honestly don't think I'd believe you. But it's pretty incredible that all of that information, all of those versions that you've just seen, they all came from the same large set of those ones and zeros, that data. We've done similar types of work with other objects as well. Tycho's supernova remnant is another supernova remnant. It's also in our Milky Way galaxy, whereas Cass A is about 10,000 light years, give or take. Tycho is a little bit further. I think we're at, 13,000 light years away from us. We're light years of distance that light travels in a year, or about 10 trillion kilometers. So again, you can see the difference between that very first observation from Chandra. This was taken, I think, only about an hour's, or no, about 10 hours worth of time that you're looking at here. And then this second observation was about 336 hours of data. And you can see what a difference it makes. And one of the benefits of having a mission like Chandra that is so mature is that you have just a treasure chest in your archive. There's just a wealth of data to explore. And again, here, the difference between that first object, the first image that I'm showing you, and the second, is that we also added a very simple star field behind us, because as much as I love data under a microscope and what I used to do, unfortunately, we have had people get confused that looking at an image like this makes them think that it could be something under a microscope versus something under a telescope. So being able to add a simple optical star field really helps set the context of an object like this. And I'm just going to take you through a few quick steps of how we process this data and some of the steps that we go through. You can see you start off with black and white, and then you add the color, you work on your smoothing and your scaling, you kind of try to understand the science of the story that you want to tell, the science that's in the published paper that the authors had worked on, and then how best to communicate that information, whether for an expert audience or a non-expert audience. And then you see the final result, in this case, this 3-colored X-ray with a simple optical star field behind it. And similarly to Cassiopeia, when you have really good data of an object like Tycho, you can essentially figure out how to model it in 3D. This is a combination of a mathematical model from Sal Orlando, who is in Italy, and it's been constrained by the X-ray observations of Chandra itself. So it's kind of a combination and a best of both worlds scenario. And you're seeing the difference between the ejecta and the shock of that supernova remnant as it's been expanding out in space. And of course, same thing, you can, once you have a 3D model, 3D print it. So I'm holding a version right here in my hand as well, and you're seeing a version being printed by one of our 3D printers. And that's the end result. It's in 2 pieces, so you can see the ejecta on the left and the shock on the right. They fit together kind of like pieces of a puzzle. And similarly, you can take it into virtual reality. We have a pretty robust virtual reality and augmented reality program that we've been working on for the Chandra X-ray Observatory. I'm really interested in sort of researching how both researchers and non-experts can use virtual reality and other kinds of extended reality, data sonification, haptic technology, even to be able to understand and interpret this information of the universe around us. Again, all from ones and zeros, and then creating materials out of that information that best tells the science story in the way that needs to be told. I'm going to end with one last example, and this is yet another supernova remnant in our Milky Way galaxy. This one is the Crab Nebula, which is another sort of famous supernova remnant, just like Tycho was also famous, and Cassiopeia is pretty famous as well. Here you're looking at the image that Chandra took back in August, I think it was August 1999, about an hour's worth of information. Right in that sort of bright white at the center is the pulsar, the core of the star after it exploded. You could essentially take the entire population of the planet and stuff them into a symbol, and that densely compacted information, that would be the same as a teaspoon of this material right here. So these are pretty powerful objects, and this one has a very fast rotation, and it's spewing out these jets and has this just gorgeous superheated disk around it. But again, 1 hour of information from 1999 versus this object, this version here, which has the X-ray data in blue, as well as infrared and optical data from Hubble and Spitzer Space Telescopes in red and purple. And you can see what a difference a few more years can make. So I believe in the second observation, we're looking at about 25 hours worth of data. Versus just 1 hour that you saw at the beginning. And similarly, this object really shines across the electromagnetic spectrum, oh, pun intended. So you can see that it's just incredible to look at in many different kinds of light, and each of those different kinds of light offers you something different to see, whether it's that stellar corpse, whether that's a high energy gas, or whether it's some of the cooler material that you would see in radio or infrared light. This, by the way, this little tiny video I showed you is actually a little piece from what's called the View Space program, and it has a number of different objects so you can slide back and forth across the multi-wavelength spectrum, so you can kind of see all the different ways that it looks in different kinds of light. And I think I have the URL on my final slide, but if not, just you can Google View Space. And with this object too, Chandra has been looking at it many times over the course of its lifespan so far. And what you're looking at here is just a short movie from the years 2000 and 2001. I think it was about 7 different observations between November and April. And you can see what an amazing amount of the dynamic rings, those wisps and the jets of matter that are around that pulsar that have been observed in the X-ray light by Chandra. Just recently, the Universal Learning Group that I work on as well worked to produce a 3D version of the Crab Nebula. This is a slightly different one. This is using some models, like the X-ray model that you're seeing here, but then also adding additional data that are more derived from the science story than like an absolute modeling in 3D itself. But you're seeing that disk and those jets and that cloud of high energy material and X-ray as it spins, and I just think this is so beautiful. unbiased, of course. And then you can see that the infrared cloud is much larger than the X-ray cloud. And that's turning around. And this was from Spitzer. And then finally, the optical or visible light, which extends even further beyond the X-ray. And you can see kind of like that hollow part where the X-ray fits in so perfectly. So they're kind of like pieces of a puzzle, and they just fit together very beautifully. And then again, as with some of our other 3D models, you can 3D print them. And this one is one of our newest. So I don't know if you can see that print on my screen, but that's what it looks like. So that's how you hold various kinds of dead stars in your hand. And we are actually working to create a version of that in augmented reality as well. And again, all of that comes from these bits and bobs, these ones and zeros, this information that had to be translated to form the visual representation of the object. So that is just a very small snippet of the type of work Chandra has been able to do over the past 20 years, and the various parts of it that I have been lucky enough to participate in. It's a very inspiring piece of equipment. I found out maybe 17 or 18 years into my work for Chandra that, you know, obviously I'm biased that these images are incredible, but also that some of the technology that went into creating telescopes like Chandra and some of its predecessors, some of that technology has had an incredible impact just on our daily lives, because getting X-ray information from the universe is pretty tricky, right? It's not an easy thing to do. To make the mirrors so smooth and so large, to make all of the various components of Chandra that had to survive in the harsh environment of space, to make the technology in order to capture that X-ray data of the universe, it was a very difficult thing to do. It was very technically challenging. The engineers, the astrophysicists, all of the people that were involved in that mission had a lot to figure out in order to make Chandra happen. And because that technology was so hard, it's perhaps not that surprising that that technology has then had quite a benefit here on Earth, even indirectly. So because it was so difficult to make some of these pieces of Chandra and other predecessors of Chandra, for example, we now know that, for example, when you're going through the airport, your baggage is being screened by technology that was developed for X-ray astronomy. And when you're at the supermarket, some of your food is screened by technology that was developed for X-ray astronomy. When you're going to, say, get a mammogram done, like I have to do a couple times a year, that technology has been improved because of telescopes like Chandra. And even when you're getting something like an MRI done, those different kinds of technologies have been improved and made safer because of the Chandra X-ray Observatory. So it was really nice getting to know that. I think for at least 17 years of my work for Chandra, I had no idea that there was such a benefit to us here on Earth as well, and that was really fun. So these are the things I get to think about and talk about all the time. I write books for fun, because I think that's also really fun to do. And if you want some of my information, to follow me on Twitter or Instagram, I like to try and engage with people with questions and answers and just conversations in general. So from here, I think I'm going to stop sharing and head it back over to Jana. And there we are.
Thank you so much. That was amazing. Give some love to our speaker.
And I stayed on time.
Excellent. We always love that.
I was amazed. I had 70 slides.
Nice.
That's a lot.
Well, I love it. It was just such a visual feast, like one after another of these amazing Chandra images. It was really quite beautiful. Yeah, so
Thank
if anybody
you.
has any questions, please think of your questions, write them in the chat. I'd like to start out, and I was kind of intrigued to hear about your background, and that you started, was it in molecular biology, and then you went into astrovisualization? And I was just wondering how that happened, or if you could say more, and the similarities and differences between those different fields.
Yeah, so, you know, it's more similar than you would think, right? I think because I've been in the sort of super macro world for so long, I really love to look back with nostalgia on the micro world that I used to get to work in. And there is actually quite a visual language that's similar between the data sets that I got to work on when it was micro versus now that I get to do when it's macro or macro. And that I think is really exciting to see. I think for both of them, you're dealing with equipment that supersedes any sort of human vision. So as soon as you're doing that, you have to create in your visual representations, you're typically doing something like adding color, whether that's micro or macro. And you have to follow the same kind of rules, that you're not creating the data just for fun or just to create something that looks pretty. You're trying to tell the scientific story, and you're doing that in a way that is to serve the science as best as you can. And in astronomy or astrophysics, you know, typically you're setting your color codes to be specific to either temperature or chemical element or something to that effect. And, you know, in the microscopy world, you're possibly doing it something slightly different, but still you're following a color code of sort, just like on the nightly news or on weather.com, you are going to color code your map by your precipitation level or by your wind speeds or whatever. But for me, the sort of bridge between those fields was computer science. And computer science was essentially the language that I needed to learn to unlock the universe, whether it was the small, tiny universe inside us or the big sort of universe that's out there beyond us. And I think really enjoy reflecting on how my past has sort of helped informed my present. It was not at all something that seemed obvious. When I was an undergrad, I was in molecular bio, and I was not like really that great at it. I struggled. I failed genetics, and I remember being mortified. Like that was the most embarrassing thing that had happened to me up till that point. And for me, computer science was just something that came very naturally. And I just am a big believer in following your strengths. And for me, that was a strength to be able to apply the coding that I learned how to do to various fields. And then once I was in X-ray astrophysics, it just seemed like a really good home for me. And it's been a wild ride. Yeah, I really liked it.
Yeah, and you get to work with all these amazing images all the time. So
I know, such a boring job. I mean, it's really a burden.
Oh, I think we have a question. Pine Dial asks, how can we be sure that we are sticking to the original images? And can you speak to the accuracy of the results in these models that you're making as compared to the original data?
Sure. So there's always going to be choices that are being made. And I should preface this by, I think there's this idea sometimes with astrophysical data sets that they are these giant selfies in the sky, right? That it's just a very cold, objective, like click, done. But it's definitely not the case. Our telescopes have been engineered by humans. The software that's required to make them run was written by humans. The data processing that has to be done to create those representations are done by humans, and humans are not perfect. Obviously, it's everything that we are understanding from the data. It's the things that we believe we're perceiving that we are then representing as best as we can. For me, the really main points, there's two things. One is to align to the scientific story as best we can, working with experts that will help to do that. And then also being true to the data to get something that is not going to be like gobbledygook. You want something that will make sense visually. So you do have to understand like a little bit of art history, if you will, how to understand a bit of color theory. It's definitely not a paint by numbers thing, but you have to make choices as a human and hope that those choices that you're making best represent the scientific story. What's also important is being very transparent. And I think a good example of this is when you're looking at, for example, a 3D model of Cassiopeia A. Now, there are, of course, many steps that have happened from those first bits of ones and zeros that came down from that telescope. It's gone through a number of transformations to lead to the two-dimensional image over time, which I didn't even show because I figured I'd run out of time, the 3D model, the 3D print, and then virtual reality. And for each of those transformations, you do have to make decisions. But I think what the important thing is to always make sure that you're still aligning it to the science as you understand it, and then also being transparent and clear on decisions that you made. So for example, with Cassiopeia A, some of the clumps that are in the representation in 3D model could not be transposed to the 3D print because they would literally fall off in a physical space than they could in a virtual space. So some of those pieces had to be removed from the model because you couldn't just have little things sticking out to denote that they might sort of be there. It didn't make any visual sense. So we had to trim it down and simplify it slightly in order to create this version. But doing that is okay as long as you're explaining that you're doing that and then saying why you're doing that. For the case of Cassiopeia A, we've since made a few different changes after working with people who are blind or visually impaired. They improved the data sets by sort of talking about how important like resolution and size and even access to the model itself were. So some of those changes have been implemented, such as a version of Cassiopeia that cuts in half. So I guess going back to your original question is how do you make sure that these are still accurate and true? You just do the best that you can. So we know that the 3D model makes sense. We know that that basic assumption of geometry was correct. We know that that observational data is there. There have actually been a few different scientific teams that have done research papers peer-reviewed on the same 3D data of Cassiopeia A and have gone on and since actually expanded upon the Tracy Delaney group's work and added to it. And so that is also another really important step. Peer review is there for a reason. And when you have multiple teams being able to either replicate and or improve upon an existing concept and an existing result, then you know that you're also still going in the right direction. So I hope that answered it. I'm not sure which part of the spectrum your question was on, but hopefully that helps.
Great. All right, let's take a question from Jim Hendrickson. The question is, has Chandra been able to contribute to multi-messenger astronomy observations to learn more about gravitational wave events?
Yes, actually, and that is a fantastic question. Thank you, Jim, for asking that. So as I mentioned very briefly at the beginning of my talk, multi-messenger astronomy has definitely become a very, very important thing for us to be able to do because you really need to have all of those different pieces in order to understand more about the world around us. You know, I love to use the idea of a baseball field or a softball field. Not that anyone could play sports right now, but when we can, you know, if we could only look at a portion of the universe and just one type of light or one type of information, you could say only see down the third base foul line, right? You wouldn't have access to the whole field, so you wouldn't know what the rules of the game were. You wouldn't know how many players were out, if there was even a ball, if you couldn't see that information. So how would you understand any of the rules of baseball or softball if your field of view was so limited? And so having not only multi-wavelength astronomy, but multi-messenger astronomy is really key to having more information to figure out that puzzle. So very exciting result from, I think it was 2008, was this gravitational wave event that likely signaled the creation of a black hole. It was a neutron star merger, and it was source GW170817, I believe. And that was, I'm pretty sure, well, our first published and publicized result, if you will, of the analysis of X-ray data in the weeks or months after that initial detection of gravitational waves. So for something like GW170817, you know, that would contain essentially the lowest mass black hole known, if that's all proven to still be true. But the critical data from Chandra, it was important to be able to determine if that neutron star merger created, like, say, a heavier neutron star or a black hole. So being able to have X-ray observations to confirm and then further the results was really important. That was a very, very exciting result to work on, by the way, even though the images themselves were just a little bit more than dots. Actually, I don't know if I could share my screen. Could I share my screen and show, or will that mess things up? I feel like I'll just leave it. But if you go to the Chandra website and Google the GW170817 results, you'll see what I'm talking about. But they're a little more than dots. However, super exciting dots. And that's the sort of result that it just makes you like sit back and just amaze yourself, because Chandra was planned in the 70s and 80s and built throughout then and into the 90s until it was launched in 99. And in that time, so much has happened. And if you fast forward to today, the field of exoplanets, the planets outside our solar system, wasn't really a thing. The first one was back in the mid 90s. And Chandra was pretty much built, or at least planned enough that, nothing would change on Chandra due to that. So to now be where we are and to have Chandra contributing to all of these scientific topics that are so cutting edge and so new and exciting, it's very, very satisfying, I think, to be part of a mission that gets to continue to learn along with you.
All right. So next question is from Nick DePalma. What is the process of tasking Chandra with targeting from object to object? So about spacecraft control.
Oh, yeah. So there are essentially superheroes that work at the Chandra Control Center. Even during coronavirus, they continue to work there, though Sabina Hurley, who is the person who oversees everything there, has done an amazing job of setting up a system that is much safer and very clean and everything done just to perfection to be able to keep everybody on the team safe from harm. So having workstations that are really far apart from each other, making sure no one touches anyone else's equipment, all of that. So many details that had to be figured out to how to operate a satellite during this very different and difficult time. So you have these crazy superheroes on the ground, these engineers and telescope operators that get to take care of Chandra just by uploading code, right? So Chandra is so far away, going a third way to the moon. Unlike Hubble, it could never be serviced. It's just too far. So everything that is ever planned for Chandra, if Chandra ever needs to visit the doctor, that doctor is just essentially code, different commands that would be uploaded to it to be able to help figure out whatever the issue is. And part of what's uploaded to Chandra every 8 hours or so through NASA's Deep Space Network includes what it's going to be looking at and how. So Chandra is really cool because it moves very slowly, like the second hand on a clock. That's called slewing, I believe. And it just essentially, it's up to the engineers and the flight operations crew to be able to plan what it's going to look at and when, in a way that is the most efficient for the system, that takes advantage of Chandra's strengths and then makes sure it doesn't play to Chandra's weaknesses, right? As a 20-year mission, any mission is going to have some weaknesses. So the operations folks are really my superheroes because they're able to do all of that from the ground, even during the coronavirus, keep everything going beautifully. And it's a field of expertise that I'm fascinated by. So I hope that answers your question, but it's a very complicated scheduling process that they have to understand what to look at when.
Mm-hmm. That's good to hear. So I think we have time just for one more question. So let's take one from...
I tend to give long answers, so I apologize.
I love it. It's very comprehensive.
I just keep going and going.
So we have a question from Elon Olson. How do you determine the different materials in the exploding stars? You mentioned that you could color code them in the AR model, but how are they categorized, differentiated, and classified?
That is a fantastic question. So what's really important is essentially that you're using spectroscopy. So Chandra has a number of instruments on board, the advanced CCD imaging spectrometer, ACES. It has the high resolution camera HRC, and it also has the low energy transmission grading and the high energy transmission grading and other parts of its spacecraft as well, of course. So all of that combined means it's not just the imaging, it's not just the images themselves that are giving you that scientific data. The spectral information, it's like the fingerprint, the DNA of the light that Chandra gets to record as well. That is really, really, really important. Having that DNA or that fingerprint of the light that's being observed. Essentially, the images are just telling you part of the story, but having the fingerprints underneath that image then gives you that information of whether it was silicon, whether it was calcium, whether it was argon or neon or whatever. So, you know, as a star is exploding, oh, I guess I don't even think I mentioned this, but, you know, as a star is exploding, the heavier elements are building up in its core, and it ends essentially around the iron mark. And once that is all iron at the core, it's just, it, you know, collapses and then it explodes. When you're looking at Cassiopeia, for example, in the model that I showed earlier, the iron was color-coded green. I'm pretty sure that one was green. So when you're seeing that iron, it's mostly on the periphery of the remnant. So you're seeing that when that star exploded, it actually turned itself inside out, right? So that's a really valuable thing to be able to visualize in a three-dimensional model. You're not only providing like a map of that supernova remnant, but you're also understanding not only how that star died, but also how that star lived, right? We can't ever look inside stars that far away, particularly, right? So when you're looking at a supernova remnant or the debris left over from a star that exploded, you're looking at the insides of a star, kind of like, you know, a pathologist would look at somebody after they pass away. So it's a really interesting way, I think, to be able to understand things like stars. And it's really important for us, right? That idea that iron in our blood and that calcium in our bones and all of those chemical elements, the only way those are created are in the furnaces of these stars, and those stellar explosions, that information, that yummy goodness is sort of, you know, recycled out into the universe, and that's how we're here. So anyways, it all comes back to us and our human point of view.
I love that, to tie it up. So thanks so much for answering our question. Sorry if we didn't get to your question, but we're going to move on to our tour. This is our virtual tour portion. So we're going to be using some Planetarium software. We have Micah coming back into view
Hi,
here.
everyone.
Hello, Micah.
Hi there.
And he's going to be driving our spaceship, and we're going to basically show you what you might see in a planetarium, but we're going to do it live stream style. And Kim is going to serve as our guide for this and show us around and show us some of these amazing objects and models that she's been talking about, but in this larger context of where we live in our kind of local corner of the universe. So first, Micah, do you want to tell us a little bit about this tool that we're using, the software, OpenSpace? Micah, I think you might be muted.
Oh,
we're getting
thank
some
you.
messages
Yeah.
that you can't hear.
Great. Okay, so I'm back. So yeah,
All right.
thank you. So I'll just
Thanks so much, everyone. So
give a quick,
so yeah, Micah, if you could go again and just tell us a little bit about OpenSpace.
The quicker summary is that this software is our data visualization software that we're making at the Museum of Natural History in New York in conjunction with 3 other universities, the University of Utah, NYU, and Linköping University in Sweden. And we're making it on a grant from NASA so that we can bring in NASA data and show it to the public and use it in conjunction with scientists to explain what's going on and to take their data and show it. And so right now we're looking at the Milky Way, and this is actually I believe a constrained simulation from the NEOJ in Japan. And we use that to contextualize other data. And so OpenSpace is all about taking different kinds of data and putting it together. And so what you're seeing here is the Milky Way, and this tiny little blue dot that you might see is representing where Earth might be. And so what we'll do here is now we can use this to turn on different data sets to explain and show different things we know. So Kim in her talk talked a lot about supernova remnants. And so what we're going to do is we're going to turn on a data set that represents locations of supernova remnants in our Milky Way. And so all of these orange dots are going to be places where we've located supernova remnants and observed them. And we have all these positions in a 3D space, like a 3D atlas. And the positions are very precise, and we know them very well at this point. And you can see, you know, all these ones are fitting mostly within the plane of the Milky Way. So what I'm going to do now is actually I'm going to turn on for us some labels, and you're going to see a lot of names and a lot of text turn on the screen. And some of them are going to look like those ones that Kim was mentioning. WO, I don't remember the number, Kim, maybe you do. But some of them have names, and so, you know, one of the names that she mentioned a lot was Cassiopeia A, and so why don't we go and take a look at that.
Oh yeah, I see it over there to the right.
So now I'll take us down there, and we've actually taken the model that Kim was showing and we brought it into the software so that we could show it in context with everything else. So now I'll turn off our labels as we come into it here, and you're going to see this this very similar or the same as one of the models that Kim showed. And here we have it in 3D space where we can now move around as you would in maybe one of her VR or AR ones. And we can see the different pieces of it colored differently. And so here, if we turn off, we can turn on and off different pieces to see how they fit. So as you mentioned, iron being green coming out of the outside. And so, Kim, can you say a little bit about different pieces? Maybe
Yeah.
how they're meant.
So this,
it ties in with what Elon was just asking, actually.
yeah, this is really exciting to see it in the Planetarium software, to be honest. I love it, and I could just stare at it and not do any speaking. But so as I mentioned earlier, you know, like spectroscopy is kind of like having like the barcode of the light, if you will. And you're looking at those various peaks of the particular wavelengths and frequencies. And so when you're looking at a model like this that's showing the iron, the silicon, the neon, the sulfur, did I say calcium? You're looking at essentially those fingerprints of where you can find them. So in this color mapping, it's not exactly the color mapping I showed before. So looking at it briefly, the green is the iron and the red is the silicon, I believe.
Yeah, that's right. I just turned off the hot silicon and the red went away. So there you go. And
okay.
then they're distinguishing between the hot and the cold as well.
Right. So each of these elements essentially produce X-rays within like a narrow range of energies, right? So you can map them through their location, essentially, of how they were created for this image, if that makes sense. So this image from Cassiopeia A, as I mentioned, we're about 10,000 light years, about 11,000 light years, give or take, from our location here on Earth. And what that does is that actually thanks. Yeah, that gives us like a really good bird's eye view of Cassiopeia A. Cassiopeia A would have exploded, well, we would have seen the explosion here on Earth maybe 350 or so years ago, give or take. And it was not noted in the historical records, or at least there's not strong evidence that it was witnessed. So perhaps it was just a very cloudy time, perhaps there was something obscuring it, who knows, but it was not one of the ones that is historically noted. However, being only about 11,000 light years away from us, it is pretty close, astronomically speaking. So
now you can see
we have
Earth.
A really good bird's eye view.
Earth shown in the blue, so you can see how far away we are.
Yep.
So now I'll turn on the, go ahead.
Oh, I just had a question. Was everything we were seeing different X-ray components then? So is that, you know, was there any portion of that would kind of correspond to the type of light that you could see with your eye, and what would you be able to see with your eye?
So there's a little bit of optical data in that 3D model, but not necessarily much that you could see with your own eye, because we're really magnifying that optical light. So yeah, nothing that great that we could see. However, you can see Cassiopeia A in optical light in a 2-dimensional image on the Chandra website if you want to see how that compares with the 3D model as well. But this model does take into consideration some of the optical information because it has been studied for so long and it is a very famous object, but it's primarily the X-ray and infrared data that you're seeing in that model.
Yeah, and of course, being able to differentiate between the different components is so important scientifically for understanding what's going on.
Right. Right, exactly. Yep. And I think so nearby, are you going to?
So let's go to Tycho now.
Tycho?
Yeah.
Okay.
And so you guys should recognize this model from her presentation, and we'll actually see it in 2 different pieces as she showed in your slide. I believe you showed a 3D print of this.
I did, yeah. So Tycho supernova remnant, do you mind if I talk over while you're doing that?
Yeah, good.
Okay, good. So Tycho supernova remnant is named because it was named after the astronomer Tycho Brahe. That was essentially the one who noted it in 1572, I believe. And this one is a little farther away than Cassiopeia A. It's about 13,000 light years, I believe. But it's still, again, you could see that it was in the sort of cosmic neighborhood of Cassiopeia A, so to speak. So it's kind of nearby. So again, we had a really good view of that. Tycho supernova remnant is a different kind of supernova remnant than Cassiopeia A. It's what's called a type 1A, which occurs when a white dwarf star essentially pulls material from or merges with a nearby companion star until this violent explosion happens and sort of obliterates everything. And that debris then goes out into space. So what you're seeing in the 3D model is that there is that shock burst, that shock waves. It's kind of like a sonic boom that you could think of like from a supersonic aircraft, for example. And then you're also seeing that clumpy kind of material, the ejecta, if you will, that stuff, the stuff that results from that explosion. So that's what you're seeing in the 2 parts of that model, which I think is really cool to see. This is a very, like I said, pretty famous object because of its historical significance. So being able to create something like that in 3D is also very, very exciting. And to be able to hold it in your hand is really cool.
So you said it was 13,000 light years away?
I think it's about 13,000 light years away.
Nice.
Yeah.
So that means that as we're observing it here, it's 13,000 years as it appeared in the past, right?
Right. Yes. I think one of the fun things, so one of the fun things about astronomy is essentially you get to be an armchair traveler, right? And you get to travel really far, essentially, without leaving your desk. So it's like you always get these, it's like the high school yearbook and you're looking back at the baby pictures of the seniors.
Now I'm going to turn on a different data set, which is a data set of pulsars. And so they'll be represented in red because you showed the pulsar of the Crab Nebula and the Crab pulsar spitting out its jets. So let's go and let's take a look at that one.
Yeah, so that's much closer to home. It's about 6,500 light years, or give or take in rounding numbers. This one was also observed from Earth, so it's another famous one with these historical ties. This one was observed in 1054 AD, I believe. At the time, its brightness would have been like Venus, right? So definitely noticeable. And it's been known, like people have seen it in the visible spectrum since like the early 18th century as well. So it's a pretty exciting object as well. And what you're seeing, that nebula, essentially, it's due to the activity of the neutron star, which is that little dot at the center inside the sort of model. That pulsar, that dot, if you will, is rotating like 30 times a second. And it's spewing out this blizzard of high energy particles. So that's what you're seeing in the disk, and also those high energy jets that appear that have sort of been like flung out over great distances from the neutron star itself. The diameter of that inner ring is about 1,000 times the diameter of our solar system. So that gives you a little bit of sense of scale, hopefully.
Yeah, scale really is one of the hardest things to demonstrate when you're out here, isn't it? Here, yeah, especially because even it's even hard to understand these kinds of scales, isn't it?
Oh, for sure. Yeah, those scales are immense. I mean, our human brains are not at all meant to understand scales of that size. And to be honest, those are kind of small things in the universe, really. So yeah, once you get out beyond to the sizes of galaxies and then to the sizes of clusters of galaxies, which can be hundreds or thousands of galaxies, yeah, human connotation, it's just not the same.
Yeah. So let's go back to something maybe that people can understand the scale of a little more, which is Earth. And we'll go back home.
So as we're going back, Kim, you've been working with Chandra since '98, is that right?
Yes.
So
yes,
did
I
you?
have.
So you were there for the launch of the spacecraft? Is that right? During that time?
Yes. Yep. I was home doing my little programming stuff, so I wasn't actually able to see see the launch, but I was too busy doing stuff. But people who were at the launch, yes, it was an incredible experience for them. Like they tell
sure
stories of like how the ground shook. Yes, very nerve-wracking. I mean, think of, it took decades to build that very beautiful but expensive piece of equipment. So to strap it into a rocket and send it off on its merry way, yeah, that was some nail-biting time right there.
Mm-hmm. Well, there's our solar system coming into view, in the inner planets' orbits. And of course, we're heading for the third one out.
Third rock from the sun.
Mm-hmm.
Yeah, and now as we come home, we're seeing an extra little orbit around Earth. And so now we can see a representation of Chandra's orbit around Earth.
So as I mentioned, Chandra goes about a third of the way to the moon. That very highly elliptical orbit that it has was for a very specific reason. It's all about efficiency and making the mission a little bit more affordable as well. But it was really important for Chandra to have as much unobstructed viewing time as possible. And so having the mission be so highly elliptical meant that it had more time to observe and less time to be essentially in the radiation belts that are around Earth. So it takes about 64 hours or so to complete one orbit. And that means that about 85% of the orbiting time is spent doing the actual recording of information. So that was a very valuable time. I think I mentioned earlier that there's just not as many X-ray photons in the universe as there are, say, optical light. So it's just harder to collect that information, and you have to look at these objects a little longer than a telescope like Hubble has to look at something that's in the visible light or near infrared or whatever. So it's really important for Chandra to have that clear view of the X-ray universe, so to speak.
Great. Well, I think that wraps up our viewing. Thank you guys so much. I just have a few more things that I would like to let everybody know about. We have a mailing list for our events, so I'm putting the link in the chat here so you guys can sign up to get notified of our future events. We are planning on doing additional live stream events in various formats. I also want to point you to skymaps.com. So just because we can't observe together with telescopes doesn't mean that you can't go outside and look at the sky. And so if you'd like to have a map of what the sky is going to look like tonight, please check that out. And you can learn to identify the constellations, or if you have binoculars, it has a list of binocular objects on there, and of course telescopic objects as well. I'm going to let you guys know about a really cool event which is happening on Monday evening, which is Astro on Tap. So this is Caltech's virtual outreach program, and so they're going to be doing a series of talks on Monday evening. It's going to be at 7:30 Pacific time, which I think is 10:30 Eastern time. So check that out. It's there in the URL bit.ly Astro on Tap. And finally, last but not least, it would really help us out if you could fill out one of our surveys. This is how we know who's coming to our events. We haven't done a lot of these virtual events, and so I'm very curious who is all here. I'd love to hear about who you are and how we can share the universe with you in a way that is fun and relevant to you. So that's tinyurl.com/Columbia Astro. And please give some love to our to Micah and to Kim, our speaker. Thank you guys so much for joining me tonight. I had a lot of fun with these excellent visualizations. So take care, everybody. Yep. Thanks everyone for coming, and we'll see you soon. Thanks.